Okay, students, good afternoon. So today my agenda is going to be few important topics, okay, that will be necessary for you in solving some equations. Okay, so we'll just get started with the presentation. Okay, so I had told you that I will be telling you about this NAND and NOR implementation. I guess all of you are very much aware, with this sort of implementation, which means any equation that is given, you could actually convert them into a NAND gate. Okay, so sometimes questions can be asked based on NAND gate, or it can be asked exclusively based on NOR gate. Okay, the reason why we use these two is because these are necessary for the implementation. Okay, the implementation with respect to uh, universal gates. Okay, fine. Now let us see step by step as to how we are going to do it. So NAND and NOR implementation. NAND and NOR gates are called universal gates, as we all know, right? Any gates can be realized using these two, both NAND and NOR. So the first one, okay, that you have to do is first step is for, let us discuss about NAND first, and then we'll talk about NOR. Okay, so there are only four steps that you need to follow. First, you have to write the logical diagram for a given expression using basic gates. So what are the basic gates? Can someone respond? Unmute and respond. Okay, science says and or not yes. So those are the basic gates. Now any equation, okay, now you all know how to realize using basic gates. So first we implement using basic gates. Then the second step is insert a not gate at the output of and. Okay, so since I'm implementing a NAND, which means I am notting the AND's output. So AND's output is negated. So I am actually putting a NOT gate at the output of and input of OR gate. This second point is very important. Okay, so output of and input of OR. Okay, so you have to make note of this point. Next, third step is if there are any double NOT gates in the same line, we can eliminate it. Why do you think so? We can eliminate it. Is it logical for us to eliminate two NOT gates in the same line? Students, I want you to respond because it's going to give the same output as original. Good. Thank you. Fine. So we can always eliminate two NOT gates. Okay, so that's the first step. Then replace all the basic gates by NAND gate. So fourth step you can do, third step you can do, first step also you can do. So most important point here is the second one, inserting NOT gate at the output of and input of OR gate. So now let us see one example. Okay, example. Uh, Realize an XOR gate, okay, using NAND gate. So what is the first step? First step is to write the equation and draw the logical diagram using basic gates, right? AB plus A bar B bar. So this is your equation and this is your implementation. I have A, I have B. So AB is multiplied here and A bar comes through this inverter, B bar comes through this inverter. and again both are multiplied and given to OR gate. Now notice I have actually drawn in pencil here. Okay, I have drawn in pencil output of NAND and input of OR. Okay, so in all these places I have to put a NOT gate. Are you able to see these small inverters that I have drawn in pencil? Yes, you're able to see this? Okay, thank you. So what is the putting these inverters was our second step, right? Now what's the next step? We need to eliminate. So I have two inverters here, so I can eliminate it. And I have two inverters here, I can eliminate it, right? And what is the final step? Replacing all the gates with NAND gate. What I do is this AND will be replaced by NAND, this AND by NAND, this NOT by NAND, this NOT also by NAND. It is just like one input NAND gate now, one input NAND gate. So this is your final implementation of NAND gate. So finally what you can also do is you can cross check. You can cross check and see if you're getting the same equation. So AB bar, because this is a NAND gate, AB bar, and here I'm going to get B bar, okay, and here I'm going to get A bar, right, A bar, B bar, A bar into B bar, and since this 2 gets multiplied, A bar into B bar, there's a bubble here, so there is one more bar, right? And again, if these two are multiplied, what is going to happen? It is going to be AB bar, this term will come here, right? And this term comes here, and a final bar. So now if you try to separate them, you should get back your original equation, right? So I think all of you have understood how to get this done. Any doubts here, students? Using De Morgan's theorem, we get the same thing because it is AB double bar plus, right? A bar, B bar, okay, again double bar. So double bar we can cancel and the bar remains. So any doubts here, students, as to how we have implemented the NAND gate? Any doubts? Any doubts with this NAND implementation? I want your response. Okay, fine. Thank you for the response, Surya. Now let us go with NOR implementation. Everything remains the same. Write the logical diagram and implement the basic gates. Insert a NOT. Second point only changes. Okay. Insert a NOT gate at the output of OR gate. But there, what were we doing? We were inserting the NOT gate at the output of AND gate. Okay, so at the output of OR gate and input of AND gate. So it is just the reverse here for your NOR realization. Then eliminate your double NOT gates and replace the gates with NOR gates, right? So let's see an example. I have even worked out here, okay, for your simplicity, and I will be sharing this uh, for your reference at the end, after the end of the session. Okay. I have a double bar, it comes here, this is how it happens, De Morgan's. So finally I get my equation. Okay, I worked it out for you. Right. Next, same XOR gate using NOR implementation mode. So I XOR, okay, this was X NOR and this is XOR, okay, A bar B plus A B bar plus A bar B. So the same thing I will be implementing using my logical diagram, okay, and I have to actually put in front of AND gate and after OR gate the NOT gates, right, an inverter. So I have two inputs here, so which means I will be putting two inverters. Then I have an OR gate here. So since I have an OR gate, I will be putting an inverter, right? So which means our second point is very important, right? NOT gate at the output and at the output of OR gate and input of AND gate, isn't it? So the same row we are following here. So once this is done, I see if any double inverters are there, okay, and I will try to replace them. So these two are my double inverters, right? So what I will eliminate them. So the remaining ones will be replaced with NOR gate. So I hope this has made your things very clear, right? So this is how you will get, you have the double bar here, double bar gets eliminated, so you get only this. Again, I use De Morgan's theorem here, I split them up, so double bar goes away here and P bar is retained. Then I use De Morgan's theorem here, addition becomes multiplication, the bar comes down, and then B has double bar can be eliminated. So don't you think this equation is the same as our question, right? So this is how you can verify, okay, you can cross check if the implementation done is correct or not. Okay. So students, any doubt with NAND and NOR implementation? Any doubt? Okay, thank you, Surya, for responding. Now, the one more thing that I wanted to tell you all is with regards to the CMOS implementation, right? So, in CMOS implementation, normally, as I've always told you, the output is always negative. Okay, so which means, um, let me just show you that, so it will be easy for you to understand. Okay, now, yeah. So now here what we have done is we have implemented y is equal to a into b plus c. Okay, this should actually be, okay, just a moment. Okay, so this can either be, the bar can either be here, okay, or the bar can be here, either one of the place. Okay, either one of the place. So it can be either on y bar, it can be y bar. If this is the equation, you'll do the same implementation, or if in case your equation is this, also will be the same. Let's say for example I do not have bar on both the side, okay, like I have what I have here. So what we have to do is we have to connect an inverter. Okay, we have to connect an inverter. So how do I connect an inverter? So you have to go back, okay, and we have a PMOS, right, and then and MOS, and then you'll be connecting the gates together, and this will be my final output. Okay, if in case there is no bar on both the side, if in case there is bar here, okay, if there is a bar there, then I don't have to draw this. Okay, or if in case, okay, there is a bar here, or if in case there is a bar here, then also you don't have to implement. Now the reason why I'm telling you this is because your CMOS inverter or your CMOS circuits will always be inverted. The outputs are always inverted. Any doubts here, students, any doubts here? So either the bar can be on left hand side or on right hand side. Okay, if there is no bar on both the sides, okay, it should actually be connected to an inverter. So what is an inverter? As we have seen here, this is an inverter. Okay, so 99.9% every equation will have a bar. It's just that I have forgotten to put here. Okay? I have forgotten to put the bar here. So is there any doubts with regards to this? Yeah, students, can you please respond? If any doubts, please ask me. Okay, so either the bar can be on your Y or the bar can be on your right hand side. Okay, either one of the places the bar will be there. So your implementation becomes the same here. Okay, this rule is important. Okay, where I had told if it's a series then you multiply, if it's parallel we add. So this is for NMOS. Can you, yes, I will be doing it today, Simon. So this is for NMOS, okay, which will multiply, and for parallel it will add. Okay, already I have posted for my first module. With regards to second module, what I will do is these are all topics from second module. The one that I just discussed, the realization. This is from second module. So what I will do is I will combine them all, and I will replace the document which is there in your Google Classroom, and I will update you all. Okay, so uh, that should be actually fine. And one more thing what I want to actually stress on is with regards to the half adder. Okay, so how many of you are aware as to what is a half adder, what is a full adder? I think you would have seen, right, many of these. Are you all aware of half adder and full adder? So this will be our last topic of discussion for the day. So we will be just seeing the adder. Okay, fine. So adders, I think you all are very much aware. Have you all studied adders? Just give me a confirmation. Yes, no. Have you all studied adders? Can someone respond? Have not studied adders? Okay, fine. So the reason why we are using an adder is because to add two bits. Okay, it is just like addition. Fine. Adding two single-bit binary values produces sum and a carry output. This operation is called half-add, and the circuit that realizes the function is called half-adder. Okay, so if a question is asked, what is a half-adder? So these lines are going to be your answer. So what is going to happen? It is going to add two binary values. Okay, and adding two single bit binary values with the inclusion of a carry input produces two outputs. So first one is called the sum and the other one is called the carry. So sum and carry concept, are you all aware of sum and carry? Okay, so if you are aware of this sum and carry, okay, so it's going to be easy, for you to understand the concept of adder. Then one more thing, two half adder circuits can be combined along with an additional gate to form a full adder. So it is just like if I want to form a full adder, then I can use two half adders. Okay, so I can combine them, half plus half, so one full half adder. Okay, so this is the truth table of your half adder. So let's say I take x, y as my inputs. Okay, and half adder normally will have only 2 bit. So I am not using C in. C in I am using only for full adder. So full adder is 3 bits. So if I have 2 bits here, so it's going to be 00, 01, 10, 11, a normal combination of 2 bits, right? No doubts here. Now 0 plus 0 will give me 0, S is sum and C out is nothing but carry. Okay, so carry gets generated only when there are two ones that are added. Okay, so I have 0 plus 0, so sum is 0 and there is no carry that has been generated. Similarly, 0 plus 1 is 1 but there is no carry. Okay. Similarly, 1 plus 0 is the same case as the previous one. I get the same thing. 1 plus 1 is a special case here. Okay. 1 plus 1 gives me 0, but a carry is generated. Okay, so this is your truth table for half adder. Now the same concept, okay, can be applied for your full adder. Okay, so 3 bit, so x y c in. Okay, so 3 zeros till 3 ones. So this is your 3 bit combination. And the same thing you can do, you know, you have sum and then you have carry. uh, 0 plus 1, 1, no carry. Okay, 1 plus 1 is actually 0 and then carry 1. Right? So let us see 3 ones here. 1 plus 1 is 0, carry is 1, and then that carry with this 1. Okay, um, so ultimately you will get 1 and 1. Sum is also 1, carry is also generated. Okay, so if a question is asked uh, with a table, explain half adder or full adder, you can use this truth table and explain. Now what can we do with regards to this table, just like how we saw for k maps? So wherever there are ones, you know, we can take them and put them in min terms. Okay, for my sum I'm getting 1 and 2, right? At value 1 and at value 2 only I have high values, right? So those are taken in the braces. And so you see out, okay, you will have high only at one case, which is 1 1, right? So that is my summation 3. So what is going to be my equation? I can directly write here, since it's a simple 2-bit, I don't have to use a keymap, right? Simple 2-bit. So this will be my x bar y, right? And it's going to be my x y bar, right? So x bar y plus x y bar. So this is nothing but your, what function is this? What function is it? Exactly. It is not XNOR, it is XOR. XOR. Okay, not XNOR. Okay. Now if you put a bar, this becomes an XNOR. This is just XOR. Okay, X bar Y plus X Y bar. So directly you can see wherever you have high, you know, those can be written here. And now let us see the case for carry out. Carry out. Now we have to check where am I getting high value for carry out. Carry out. I'm getting high value here, and this is at 1 1. So which means that X Y. Okay, C out is equal to xy. Now simple, what you can do is you can implement it using your logic gates, or you can even use your NAND implementation and you can do it, right? So you have a direct gate here, XOR performing function, right? A basic gate, a special purpose function. So xy you have, and that is going to give you your sum. C out you have a multiplication, so you're using an AND gate. Okay, x y, and that gives you your C out. So this complete thing is your half adder. Now you can even implement the uh, functionality here. Okay, with respect, so if I have to split this up, okay, if I have to split, then you know I can even use this kind of representation. Okay, x y bar, because it's passing through an inverter, so y bar. Okay, then x bar y, so I get a sum here. So this is exclusively using only the basic gates. If I'm using an XOR gate directly, then it is simple, right? So either of the way you can implement your half adder. Next, for your full adder, what you're going to do, you'll have the equations. You're going to see wherever you have ones. So I have 1 at 1, 2, 4, and 7, right? 1, 2, 4, 7. Similarly, I look for C out. I plot in the key map. I value the squares. I just put the ones in whichever value it is. Okay, then I try to do my grouping, right? So is any grouping possible here? Because they all are separated, so there's no grouping possible, right? So here grouping is possible because they are together. So I get xy, I get yc in, and then I get xc in. So this is going to be my carry out equation, which is xy plus xc in plus yc in, right? And my sum is going to be single. Okay, it is going to be single. There is no grouping here. So you're going to get 1 2 3 4 four equations, 1 2 3 4, right? So if you compare this, okay, this is nothing but your XOR function. So you can write it as x is XORed with y and XORed with c in. Okay. So this is what I wanted to discuss for today's class. And these are some different implementations, full adder logic diagrams. Okay, you can even implement it using your basic functions. Basic gates x bar y bar c in, right? X bar y bar c in, multiply through an AND gate. Then you take the next term, x bar y c in bar, x bar y c in bar, and then finally I have to add them all. So finally I'm going to add them all. Then for my c out also, xy xc in yc in. So this is also given, right? Now here uh, I have used a Boolean algebra here for your explanation point of view. Okay, and I can even write it using my XOR function. Okay, so let's see it one by one. Xy, then xc. Okay, so since I do not have y, what I will do is I want y because the other term is here. So yc, then x and x bar. Okay, so meanwhile I will multiply them. Okay, I will multiply them and I will get these equations. Then I will take them common. So 1 plus anything gives me only xy, right? Then these terms are again taken down. Then xy is here. Then c is common between these. So I take c. Then xy bar plus x bar y. So this is nothing but x is XORed with y. So this is another representation of your full ladder C out equation. Okay, C out equation normally is xy, xc in plus yc in. See, there are n number of things that you can actually play with your digital electronics. Okay, once you have the equation, k-map, functions, you can actually do them. So this is how your sum is implemented. So your sum is nothing but x and y and c in all are XORed, right? We have x, y, XORed, then c in. So these are given as sum. Now if you want to multiply them, then it is xy, then x c in, and then y c in is here, and then y is here. So y c in, c out. So if you want to implement, okay, using your uh, half adder, sometimes question will be asked, using two half adders implement a full adder. So in that case I can use this type of function. Okay, this is just for your understanding. So xy is here. Okay, and then it goes with c in, just like what I've done here. Okay, c in plus x is XORed with y, so that is my sum. And c out is nothing but xy plus c, the same equation here, xy c, x is XORed with y, the same equation is here. Okay, so you can verify this. Okay, you can verify this uh, using the expanded equation here. So students, any doubts with regards to your adders, with regards to CMOS logic, with regards to NAND and NOR implementation? Any doubts you have, you can ask me. Okay, right, fine. So in the remaining classes, okay, the upcoming classes, we will see some advanced topics as well as to how we can minimize, how we can um, use them, and we have some multiplexers. Okay, we have encoders, priority encoders. So all this we will see in upcoming classes.